Alrighty, gang, welcome back. Let me close my door here real quick. Welcome back and welcome to the last lecture in MAC 1140. You guys have been troopers, hanging in there, grinding stuff out. I'm very, very proud of you. Like I said, today, last lecture. That's a bit of a fib, if I'm honest. So today we're going to finish the material on linear algebra. We're going to finish our kind of little foray into systems and matrices. There is going to be one more little lecture that I'm going to post for you on sequences and series. It's really just about notation. I want to make sure that you guys are exposed to a certain type of notation and a certain little concept before I leave you. Not because it's something that you're going to do all the time in calculus, but because it's something that you're going to see at one part of Calc 1. And that one part of Calc 1, folks who struggle are the people usually who don't get exposed to that notation. And then you will see it a lot in Calc 2 also. But for today, that's not relevant. Today, we are going to be talking about matrices again. Let's get this up. Get this connected. And we can get started. We need to talk a little bit about your tests. So this, of course, is MAC 1140. Section number is 008. That is a pre-calc class. Today is the 2nd of December, 2021. Today we're talking about matrix inverses. Solving the matrix equation AX equals B. And this is coming from section 10.5. So before we get there, announcement-y stuff. I did mention this before, I just want to say it again. Exam 4 is going to be a take-home. What that means is rather than being like a timed test in Canvas, I am going to give you a PDF. You must print the PDF. Then scan and upload to the Canvas assignment. Titled Exam 4. There is going to be an honor pledge on this, and the basic rules here are you can use your notes in your book, but no other sources. Including people. So you cannot talk to a tutor about this. You cannot talk with your classmates about this. Your notes in your textbook are okay to use, but nothing else. I want to emphasize the other people thing and also like apps. I have Mathway, Photomath, Symbolab, all that shit. And I, of course, run my own tests through those. And if you take a solution from one of those places, I will know. The sort of natural workflow based on the way I've taught you guys how to do things is very different from the way those apps do things. So just a little heads up, warning ahead of time. I know what that shit looks like. I know what real solutions look like. Please just do the natural real thing. Yes, so the other option, you can also complete it digitally, right? So if you have a tablet or an iPad, touchscreen, laptop, something like that, and you want to complete this digitally, and then save the completed PDF and upload that, I'm totally fine with that. No problems there. The important thing is that, like the Jello, we preserve the formatting. So what I don't want you to do not just write the problems on a piece of notebook paper and then give me a scan of that or a picture of that. That's no good. Office hours tomorrow. Yeah, planning to do regular office hours tomorrow. I know office hours yesterday. Let's see, I think, is she here? I was only able to work with one person during the office hours yesterday because I had an arrangement made with her ahead of time to do a makeup test, but I had a bunch of shit going on yesterday that kept me from being able to do the normal office hour thing. Yeah, so another good question. If you have a question about the test and you're like thinking, this is something I want to ask a tutor or I want to ask a classmate, ask me. Totally, definitely ask me. Right? During an actual exam, you guys are allowed to ask me questions, right? And sometimes I'll answer them with more detail or less detail. But for sure, if you're tempted to reach out to a source or Google something or talk to a tutor or talk to a classmate, instead of doing any of that, just reach out to me. Right? I'll give you a little hint, little nudge in the right direction. And that way you don't have to worry about getting in trouble for cheating, but you can still get a little bit of help. All right, the take home is due by the start of the final. Which for your class, so your guys' final is on the 9th at 10:30 a.m.
Can I ask a question about the final?
Sure.
Are we able to take that in the testing center like we have with the other exams, or are we going to need to do that?
I'm glad you asked. So the final exam we cannot do in the testing center. The testing center is kind of the designated spot for fully online classes to do their finals. And because the college requires that the final exam be taken like at an exact time, we can't do like the all-day walk-in thing. So no, the final exam, you will have to take it online with me. And that means you're going to need Zoom on your phone and HonorLock on your computer. Also a reliable internet connection. So this is actually probably worth putting in writing also. So one last thing before I write this down. Just want to reiterate, exam 4, the take-home test, is due at the start of the final exam. So the latest I will take exam 4 is 10:30 a.m. on December 9th. If you finish it before then, by all means, submit it. Go ahead, don't stress. But the absolute latest I can accept exam 4 is the 9th at 10:30 a.m. Okay, note on the final. Cannot take the final at the testing center. They're just too busy. It must be done online with me. This means Zoom on your phone and HonorLock on your PC. If you know, for example, that your internet is shoddy at home, or if you know that you've had your laptop can't run HonorLock for whatever reason, something like that, please start working on a solution to those issues now. The college has a laptop loan program, so if you don't have a computer that you can run HonorLock on, right, this is the form to ask to loan a laptop. I'll paste that in the chat. So if you need to borrow a laptop for the final, please go ahead and fill out this form like today, like as soon as you possibly can. Usually people who need these do them at the start of the semester. I don't know how many computers they have available at the moment, but I expect that the stash will get a little bit short. So if you know for sure that you're going to need a different laptop or computer than what you have at home or available to you, please go ahead and talk to them like immediately. Test 3 grades, I'm getting there. I went by the testing center this morning to retrieve the papers from them, And I am grinding out some Calc 2 tests at the moment. As soon as I finish those, I will move to your test 3 stuff. It's the end of the term, and it's hard to not get things a little bit piled up here. Certainly they will be done before the final. That is the best promise I can make 100% for sure, is that your exam 3 grades will be done before you have to sit down for the final exam. Okay, so cannot take the final at the testing center, must be done online with me, which means you need Zoom on your phone and you need honor lock on your computer. If there's any technology problems there, good internet access, laptop issues, phone issues, reach out to me ahead of time, like right now, as soon as we can, and we'll start working on those. I can find a phone or a laptop or something for you to use if you don't have it. All right. That's all. Let me remind you kind of where we are in terms of the chapter 10 stuff. A system of equations like, I don't know, I'm just going to make something up. 3x minus 2y plus z equals 0, x plus y minus z equals 1, and negative x plus 2y plus z equals negative 1 can be expressed as a matrix equation ax equals b, where A is the regular coefficient matrix, which for this system would be 3, negative 2, 1, 1, 1, negative 1, negative 1, 2, 1. So not the augmented coefficient matrix, just the regular coefficient matrix. X, try to make clear capital X. X would be the 3 by 1 column matrix here, whose entries are just little x, little y, and little z. And B is the 3 by 1 column matrix of the right-hand sides, 0, 1, negative 1. At the end of class last time, we saw that if you write down this equation, ax equals b, that's this matrix times this matrix equals this matrix. And then you multiply this times this, what you get is a 3 by 1 whose first row is this, whose first entry is this, whose second entry is this, and whose third entry is this. So in order for that product, a times x, to be equal to b, you would need all 3 of these equations to be true. What we would like to do is solve this matrix equation staying in matrix land. So today, we learn to solve the matrix equation ax equals b by, and I'm going to put this in some little quote bunnies here, by dividing both sides by the matrix capital A. Now, we've seen that matrix multiplication is pretty complicated. Matrix division is not even a thing. And that's why I'm putting this in quote bunnies, because like dividing by, right? It's not really a thing we can do. But there is something kind of like division for matrices. The matrices that you can divide by are square matrices with a certain property called non-singular. The way we're going to get there, I'm going to come back and talk about real numbers for a minute and kind of discuss how to understand division in the setting of a ring is really the way to say it rather than a field. Try to understand kind of what division is for the real numbers in a way that can be generalized to matrices. Because matrices do not form a field, we can't really talk about division in the normal fashion. But they do form a ring with unity. And it is that concept of unity that we're going to talk about now. So we're going to get into this. I'll turn this off to get it out of the way. Let's do it. Kind of the core idea behind the process of division is the concept of a reciprocal. For a real number, let me use little a. Dividing by a is the same as multiplying by 1 over a, or the reciprocal of a, which, it can be written as a power like this. So this is kind of the first thing, right? If I want to kind of describe division, which is not a thing for matrices, in terms of multiplication, which is a thing for matrices, the first step is to see how I could describe division for real numbers in terms of multiplication. And then the idea is going to be, well, okay, if I have a matrix, capital A, can I find another matrix, capital A to the -1, or capital A inverse, we'll call it, that behaves the same way as, A to the -1 does for a real number A? And the answer there is going to be yes. One way to characterize, that means totally describe, one way to totally describe this negative first power of the number A is to say A to the -1 times A is always going to be equal to 1. So if I want to describe the reciprocal of a number, like 1/5 to 5 or 1/10 to 10, one way to kind of define what that reciprocal is to say, well, it's the thing such that when you multiply by the original number, you get 1. There are names for this. This is called the multiplicative inverse. In an advanced algebra class, we call this the when you're thinking about multiplication, it is the thing that undoes multiplication by A. And in terms of abstract algebra, again, the number 1 can be called the multiplicative identity. And we call it that, the identity element, because when you multiply any number by 1, you get that number back. So what I want to do, this looks like something I could rewrite in terms of matrices, right? If I just change these to capital A's, I could say, okay, and that will let me talk about this inverse or multiplicative inverse or reciprocal, if you like, of the matrix A. The challenge is I don't have a concept of 1 for matrices. So to discuss multiplicative inverses, aka division, for matrices, we need, right, if this is the equation that defines what a reciprocal or multiplicative inverse is, then I need a matrix that kind of acts the same way the number 1 acts. We need a matrix version of the number 1. So again, what makes the number 1 special? Why do we call it the multiplicative identity? Well, because when you multiply any number by the number 1, you get that number you started with back. That's what makes the number 1 special. So that is, we seek a matrix instead of calling it 1, I'll call it I for identity, such that A times I is always going to be A. So if you multiply A by I on the right, you get A back, right? Just like some number times 1 is always that number. And I times A is always A. Remember, matrix multiplication is not commutative. All right, so it's possible that you multiply on the right and get A back, but maybe when you multiply on the left, you get something else. We don't want that. This matrix I will be the matrix version of the number 1. Now remember, you can't just go multiplying any 2 matrices. There's that size condition, right? You can only multiply a matrix A times another matrix B if the length of the rows of A is the same as the length of the columns of B, because of the way matrix multiplication is defined. What that means is there's not going to be one matrix I which does this. We'll have to have many matrices I which do this for various sizes. It turns out that for each n, there is a matrix called IN, which does this. Now, I1, that would be a 1 by 1 matrix. That's just the number 1. I2 is the 2 by 2 matrix 1, 0, 0, 1. I3 is the 3 by 3 matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And you get where this is going, right? I4 is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And these are called the identity matrices. So if I take any 2 by 2 matrix A and I multiply it by I2, I'll get my matrix A back. And it doesn't matter which side I multiply on. If I take any 3 by 3 matrix A and I multiply it by I3, I will get my matrix A back. If I take any 4 by 4A, multiply by I4, and so on, you get the idea. These are called the identity matrices. And we just write I instead of like I2, I3, when the size is understood through the context. Right, so if I'm working with a 2 by 2 matrix A, and I want to talk about the multiplicative identity associated with that matrix, I wouldn't write I2, I would just write I. You can write I2 if you want, it just helps things seem less cluttered. I want to verify that these matrices do what they're supposed to do. So I'm going to give myself a 2 by 2 matrix A, a 3 by 3 matrix A, and I'll multiply the 2 by 2 by I2, I'll multiply the 3 by 3 by I3, and show you that you really do get your original matrix back. So sort of this is the big deal behind this discussion. That if A is any matrix and I is the appropriately sized identity matrix, then A times I will be A and I times A will be A. And this will allow me to define an inverse. All right. Yes, let's grab some examples. And just verify that these identity matrices do the thing they're supposed to do. Let's let A be the 2 by 2 matrix, 2, -1, 3, 5, and verify that IA equals A times I. That when you multiply by the 2 by 2 identity, you get your matrix A back. So I times A would be 1, 0, 0, 1. That's I2 times 2, -1, 3, 5. And if I do this matrix multiplication, these are both 2 by 2s, so I'm going to get another 2 by 2 out. Remember how it works. You take rows of the first with columns of the second. So this is 1 times 2 plus 0 times 3. That's what goes in my 1, 1 position. To find what goes in my 1, 2 position, I take row 1 and column 2. That's 1 times -1 plus 0 times 5. To find out what goes in my 2, 1 position, I take the second row and the first column. So that's 0 times 2 plus 1 times 3. And to find out what goes in my 2, 2 position, I take the second row and second column. So that's 0 times -1 plus 1 times 5. And just simplifying each of these things, this is 1 plus, or sorry, this is 2 plus 0. That's 2. This is -1 plus 0, which is -1. This is 0 plus 3, which is 3. And this is 0 plus 5, which is 5. And lo and behold, the matrix I got out is the same as the matrix A that we started with. So yeah, I times A is equal to A. And hopefully you can kind of see how this works. This first row being 1, 0 says when I whack this row against this column, it's going to return 1 times this plus 0 times this, which means it's going to preserve the 2 in the 1, 1 position. If I whack this first row and this second column together, it's going to take 1 times this plus 0 times this. In other words, it's going to preserve the 1, 2 position. And this is why the identity matrices look the way they do. Let's calculate A times I, because we've seen that sometimes changing the order of multiplication changes the answer. So if I write A first, that's 2, -1, 3, 5. And I2 is 1, 0, 0, 1. And I'll do the same thing. So rows of the first with columns of the second. That's 2 times 1 plus -1 times 0. And then in my 1, 2 position, that's 2 times 0 plus -1 times 1. In my 2, 1 position, that's 3 times 1 plus 5 times 0. And in my 2, 2 position, that's 3 times 0 plus 5 times 1. And again, if you clean this up, this is 2 minus 0, which is 2. This is 0 minus 1, which is -1. This is 3 plus 0, which is 3. And this is 0 plus 5, which is 5. So, yep, she works. There are deeper ways of thinking about matrix multiplication. The second matrix here you can think of as kind of choosing how much to multiply each entry in the row over here by when you combine them. So this says you're going to take one copy of the first term and 0 copies of the second term and put that in the 1, 1 position. Well, of course, that's going to preserve this too. We can do it for a 3 by 3 also. Maybe I'll just do one direction here. Let A be, how about the 3 by 3 we started with? 3, 2, oh, sorry, 3, negative 2, 1, 1, 1, negative 1, negative 1, 2, 1. And verify that A times I equals A. I'll just do it the one way because multiplying 3 by 3s takes a little bit of time. Well, okay, A times I, here I is I3, so we're talking about a 3 by 3 matrix A. That's 3, negative 2, 1, 1, 1, negative 1, negative 1, 2, 1, times the 3 by 3 identity, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And when I calculate this matrix product, I'll get another 3 by 3, whose 1, 1 entry comes from the first row here and the first column here. So this is 3 times 1 minus 2 times 0 plus 1 times 0. The 1, 2 entry comes from row 1, column 2. That's 3 times 0 minus 2 times 1 plus 1 times 0. And the 1, 3 entry comes from row 1, column 3. That's 3 times 0 minus 2 times 0 plus 1 times 1. Moving to row 2, the 2, 1 position comes from 1 times 1 plus 1 times 0 minus 1 times 0. Plus 1 times 0 minus 1 times 0. The 2, 2 position comes from row 2, column 2. That's 0 times 1 plus 1 times 1 plus 1 times 0. And the 2, 3 position comes from row 2, column 3. So that's 1 times 0 plus 1 times 0 minus 1 times 1. And now the same thing in the third row. Take this row and this column. That's negative 1 times 1 plus 2 times 0 plus 1 times 0. 2 times 0 plus 1 times 0. And then row 3, column 2 is negative 1 times 0 plus 2 times 1 plus 1 times 0. And then for this position, I take row 3, column 3. That's negative 1 times 0 plus 2 times 0 plus 1 times 1. And this is our resulting matrix, which we can simplify. This is 3 minus 0 plus 0 is just 3. This is 0 minus 2 plus 0 is just minus 2. This is 0 minus 0 plus 1 is just 1. This is 1 plus 0 minus 0 is just 1. This is 0 plus 1 minus 0, which is just 1. This is 0 plus 0 minus 1, which is negative 1. This is negative 1 plus 0 plus 0 is just negative 1. 0 plus 2 plus 0 is 2. And 0 plus 0 plus 1 is 1. And if we compare that to the original matrix A, you see it's the same thing. And you could check that if you multiplied in the other direction, you would again get A. I'm not going to take the time to do it because again, multiplying 3 by 3s takes a while. these matrices I that have ones on the main diagonal and zeros everywhere else are called identity matrices. And they're called that because if you take any matrix and multiply it by I, you get that matrix back. With this in mind, how do you think we could define an inverse of a matrix? So I really acts like the number one in the sense that when you multiply any matrix by I, you get that matrix back. So keeping that in mind, right? How do you think we could define the reciprocal or inverse of a matrix? For real numbers, it's like this, right? The reciprocal or multiplicative inverse is the number such that when you multiply that number by the original number, you get 1. Right? This is the thing that allows us to divide by A, is multiplying by the reciprocal. And the reciprocal is defined to be this new number such that when you multiply it by the old number, you get 1. So now I have a matrix that acts like the number 1, this matrix I. If I want to define the reciprocal of a matrix, that would be just this, with everything replaced by its matrix version. Plus, to divide by a matrix, we would multiply by its, we call it an inverse in matrix land. We multiply by it by A inverse, where A inverse is the matrix defined to satisfy A inverse times A equals I, and A times A inverse equals I. So this is the definition of the inverse of a matrix. Given a matrix A, the inverse to that matrix is the matrix denoted A inverse like this, which satisfies these two equations. When you multiply A and A inverse in either order, you get the matrix version of the number 1, the identity. Finding the inverse is a challenge all on its own. And we'll get there. In fact, I guess that's what we're going to do now. We could write down a matrix and its inverse and try to verify that it does the thing it should do. First, crack open your book here to get some nice examples. If I just go making these up, they'll be pretty nasty. Let's see, verifying an inverse. Oh, yeah, here we are. So first, any questions on these definitions? The definition of the identity matrix, the definition of an inverse matrix. Why we call the identity, anything like that. Okay. And let's start simple. Are the matrices, I'll call them A and B. A is 2, -1, -7, 4. And B that's going to be a little nasty, isn't it? Yeah, okay. 7 halves. Really? Oh, no, not that one. That's the wrong one. Yeah, okay. And 4, 1, 7, 2 inverses. Yeah. In other words, is B equal to A inverse? What should I check if I want to answer this question? Are these two matrices inverses of each other? What am I asking? I'm asking, is this true? Right? When I multiply those two matrices, do I get the identity? So let's check. AB here, that's 2, -1, -7, 4 times 4, 1, 7, 2. Well, let's go ahead and do that multiplication and see what we get. Row 1, column 2, that's 2 times 4 minus 1 times 7. Row 1, column 2, that's 2 times 1 minus 1 times 2. Row 2, column 1, that's -7 times 4 plus 4 times 7. And row 2, column 2, that's -7 times 1 plus 4 times 2. Well, this is 8 minus 7, which is 1. This is 2 minus 2, which is 0. This is -28 plus 28, which is 0. And this is -7 plus 8, which is 1. And yeah, that's the identity, right? That's I2, or just I. And if I multiply them in the other order, that's 4, 1, 7, 2 times 2, -1, -7, 4. That's 4 times 2 plus 1 times -7. 4 times -1 plus 1 times 4. 7 times 2 minus 2 times 7. And 7 times -1 plus 2 times 4. And again, this is 8 minus 7, which is 1. This is -4 plus 4, which is 0. This is 14 minus 14, which is 0. And this is -7 plus 8, which is +1. So yeah, this is also the identity. So yes, B is A inverse. So if I give you two matrices and ask you, are these inverses? Your job is to compute the product, right? Multiply those matrices in both order and see if you get the identity both times. If you do, then yes, those are inverses. If you don't, then no, those are not inverses. So the big question comes now, given a matrix A, how do you find its inverse? And the answer here is first you augment the matrix A by the appropriate sized identity. Then you perform row operations until the identity is on the left-hand side. So first you write the matrix A augmented by the matrix I. And then you do row operations until the matrix I shows up on the left. And then what will be over here on the right is A inverse. This is how you find the inverse of a matrix. So let me do it for the matrix we just worked with. We already know that 4172 is the inverse of the matrix 2, -1, -7, 4, because we just checked that. Let's see if we can come up with this. Well, if I write down A augmented by the identity, that's 2, -1, 1, 0, -7, 4, 0, 1. Anytime I write an augmented matrix, I'll always put that bar there. And what I need to do is perform row operations until the thing on the left is the identity. So I want to turn this into the identity 1, 0, 0, 1. And then the thing that shows up over here through that process will be the inverse matrix. All right. Well, to turn this into the identity, I need ones here and here. I need zeros here and here. Let me start by making this a 1, because I don't see any obvious way to kill this guy at the moment. So first thing I'll do is multiply through row 1 by 1/2. So my new row 1 is going to be 1/2 times my old row 1. That's going to give me 1, negative 1/2, positive 1/2, 0. And row 2 doesn't change. Negative 7, 4, 0, 1. Now I need to make this a 0. So my new row 2 will be my old row 2 plus 7 copies of old row 1. That'll do it, right? If I multiply this row by 7 and add to this row. I'm gonna have to do some arithmetic with fractions, but first row 1 doesn't change. Seven times 1 plus 7 plus negative 7 is 0. 7 times negative 1/2 is negative 7/2. Negative 7 over 2 plus 4, you can do it off to the side if you want, is negative 7 over 2 plus 8 over 2 is positive 1/2. So this guy down here is going to become a positive 1/2. Seven times 1/2 is 7/2 plus 0 is 7/2. And 7 times 0 is 0 plus 1 is 1. Okay. Other things I need to do, I need to make this a 0, and I need to make this a 1. And the smart move is to make this a 0 first. While we're doing these row, the idea is to do the row operations on this whole augmented matrix. So remember when we first started doing row operations on matrices, we were trying to put the system into triangular form. So anytime you do a row operation on a matrix, you do it on the whole row. It's like when I multiply through row 1 by 1/2 here, I multiply this whole row by 1/2, not just these pieces. That's the idea. And the kind of concept here is that by doing the row operations to make this into the identity, the thing over here, which starts out as the identity, will turn into the inverse. So by turning this into 1, 0, 0, 1, I will automatically turn this into the inverse matrix. That's what we want. So definitely important that we're doing these row operations to both pieces of the matrix, both sides of the augmentation bar. Now the specifics of how these numbers are changing is just the arithmetic. This first row operation, I multiplied everything in row 1 by 1/2. That gave me 1, because 1/2 times 2 is 1. Negative 1 times 1/2 is negative 1/2. Positive 1 times 1/2 is positive 1/2. And 0 times 1/2 is 0. And we have to do it to the whole row. That's the idea. And then for my next step, I multiplied this by 7 and added it to this. In other words, I added 7 times row 1 to row 2. 7 times 1 is negative 7 plus negative, 7 times 1 is 7 plus negative 7 is 0. 7 times negative 1/2 is negative 7/2 plus 4. I did the arithmetic over here, is 1/2. 7 times 1/2 is 7/2 plus 0 is 7/2. And 7 times 0 is 0 plus 1 is still 1. So for my next trick, I will kill the negative 1/2 that is in the 2 or in the 1, 2 position. I'm going to make this a 0. I'm going to do that just by saying my new row 1 is old row 1 plus old row 2. That will, adding this to this will make that 0. And since this is already a 0, this will stay a 1, which is what I want. So first let me copy down the row that doesn't change. 0, 1/2, 7/2, 1. And then when I do this row operation, I'm going to add 0 to 1. That stays 1. Add 1/2 to negative 1/2. That is 0. I'm going to add 7/2 to 1/2. That's 8/2, which is 4. And then I'm going to add 1 to 0, which is 1. And now we're almost done. I almost have my identity matrix here. I've got a 1 here, a 0 here, a 0 here. I just need a 1 here. And I can get that if I multiply through row 2 by 2. So my final row operation here is that my new row 2 is 2 times my old row 2. And when I do that, row 1 stays 1, 0, 4, 1. Row 2 becomes 0, 1, 7, 2. So now that this is the matrix I, the identity matrix, this must be the matrix A inverse. In other words, A inverse is the 2 by 2, 4, 1, 7, 2, which is what we saw, right? This is our answer. And we knew that that should be our answer because we just verified in our previous problem that 4172 is the inverse of this guy. So I'm just showing you the procedure here. It's up to you what row operations to do in what order. I recommend doing them in the order we've discussed. So making this a 1, then making everything beneath it a 0, and continuing like that until you get your regular row echelon form. Then make all the other diagonals a 1 and start clearing out things above. So I recommend going in the order I'm going in here. But you can do it in whatever order you want. Yeah. So sort of let me give you a little procedure to follow. The normal order to do these row operations when row reducing, like whether you're trying to get to the regular echelon form or the reduced row echelon form, just say you have a matrix here like A11, A12, A13. I'll set it up as a 3 by 3 to start. A21, A22, A23, A31, A32, A33. So normally, first, you want to go one column at a time. You want to make these 0. And this one. Sometimes you'll make this guy 1 first and then make these 0. Sometimes it's convenient to make these 0 first and then this 1. It just depends on the arithmetic. And that takes care of your first column. Then you make the 2, 2 position. I'll say it like this: the 3, 2 position 0. And this 1. Label these, number them. Now make the 3, 3 position 1. And I'm going to make these guys, all of these, 0. That's the normal order to do this stuff. So you work one column at a time, making this one and everything beneath him 0. Then you move to column 2, you make this a 1 and this a 0. Then you move to column 3, you start by making this a 1 and then everything above him 0. And then lastly, you usually make this 0. Sometimes you get lucky and you get some things for free as you go through this procedure. Like maybe as you make this a 0, this becomes a 0 also. Or maybe as you're doing some of the work for column 1, this becomes a 0 or this becomes a 1. But this is sort of the general procedure. And for larger matrices, it's the same thing. You go one column at a time, making that top entry a 1, then everything down there 0. Then you move to column 2, making the second entry a 1 and everything beneath it 0. This procedure is outlined in your textbook as Gauss-Jordan elimination. And again, it's not necessary to go in this order, but this is sort of the, if you go in this order, you will save time because it guarantees you don't undo any of your work as you try to do other stuff. Okay. So what I'd like to do now is solve a linear system. And I'm going to take it from this previous example. By solving the associated matrix equation. AX equals B. So if I want to rewrite this system as AX equals B, that would be the matrix A is 2, -1, 3, 5. Oh wait, no, this is the wrong one. I'm so sorry. Where's the one that we calculated the inverse for? So sorry. Yeah, let me. The matrix I just wrote down is singular. Change that example a little bit. We're going to solve the system 2x minus y equals 3 and -7x plus 4y equals -1 by solving the associated matrix equation AX equals B. Sorry, gotta pick these examples carefully. Okay. So the matrix A here would be 2, -1, -7, 4. It's that matrix whose inverse we found a minute ago. X is the thing we're going to try to solve for. It's the column matrix, just XY. And B is the column matrix coming from the right-hand side, 3, -1. So with these choices for A, X, and B, then the matrix equation AX equals B is equivalent to this system. Is equivalent to 2x minus y equals 3, and negative 7x plus 4y equals negative 1. And we previously found and verified that A inverse is the matrix 4, 1, 7, 2. All right, so with all this stuff tucked in our pocket, watch how quickly we can solve this system. I haven't done any work to solve the system so far. I'm just describing what we're doing. Here we go. We're going to solve the system in one step. Now, AX equals B is equivalent to, I said I would like to divide by A, which means I'm going to multiply by A inverse. I'm going to do so on the left-hand side because I want that A inverse to run into the matrix A, not the matrix X. So that means on both sides, I apply A inverse on the left. Remember, matrix multiplication, while it is not commutative, it is associative. So whether I'm thinking of this as AX with A inverse over here, that's the same as saying A inverse times A times X. What is A inverse times A?
Is it 1, 0, 0, 1?
Yeah, it's the, I'll just write it as I. It's the identity matrix. So my left-hand side is now I times X equals A inverse times B. What is I times X? Good, it's just X, right? By definition, I times any matrix is just that matrix. So this is just X equals A inverse B. You just solved the system. Now I want to know what are the entries here? So A inverse is 4, 1, 7, 2. And B, my column of right-hand side was 3, negative 1. So when I do this matrix multiplication, I will get another matrix of the same size as this guy, a 2 by 1. And his entries will be 4 times 3 plus 1 times negative 1. It's 12 minus 1. And 7 times 3 minus 2 is 21 minus 2. In other words, this is 11, 11, 19. So little x is 11 and little y is 19. In other words, the ordered pair that I'm looking for is 11, 19. Done. Pretty badass, right? Single computation does the whole thing. No substitution, no elimination, nada. If you have the inverse of your coefficient matrix, then you can solve the whole system, which is equivalent to AX equals B, just by multiplying on both sides by that inverse matrix. The only calculation you need to do is actually computing A inverse times B. Boom, and that's your answer.
How did you get 12 minus 1 and 21 minus 2?
Just doing the matrix product. So 4 times 3 plus 1 times negative 1. That's 12 plus negative 1, or 12 minus 1. And 7 times 3 plus 2 times negative 1 is 21 minus 2.
Okay, that makes sense. Thank you.
Yeah, no worries. Just those rules for matrix multiplication. It's weird. Matrix products take practice, but it'll feel more natural with time. So yeah, for me, this is pretty badass, right? If I can take a system of equations and solve it in a single step without doing any elimination, backsub, all that crap, I'm a real happy camper. Now, the catch is, you may have guessed this, in mathematics, there's no free lunch, right? You never get something for nothing in math. Finding this inverse matrix is exactly as much work as doing the elimination for the original system, right? If you look at the work we did to find this inverse, it really amounted to taking the original matrix and row reducing it all the way. And that's what gave us the inverse. So unless you have a speedy trick to find the inverse of a matrix, this procedure doesn't really save you any time. Now, luckily, there are speedy tricks to finding the inverses for some matrices. What I want to do next is invert a 3x3 for you. Let me see, how am I doing on time? 12. Ooh, we're just about out of time. So yeah, let me see this. Finding A inverse by that procedure where you take A and augment by I, and then row reduce until you have I over here. And that means A inverse is here. Takes time. Takes exactly as much time as solving the system other ways. So to make this procedure valuable, we want a speedy trick to find A inverse. And for 2x2s, there is a speedy trick. You may have noticed this. If A is the 2x2 matrix A, B, C, D, then as long as something called the determinant, AD minus CB, is not equal to 0, then A has an inverse and A inverse is equal to 1 over that number, AD minus CB, times the new matrix you get by swapping A and D and negating C and B. So that would be D, negative B, negative C, A. This yields by far the fastest solution to any 2x2 system. Unfortunately, for 3x3s and larger, there really isn't a speedy path. You just have to go through this process. Sometimes this process isn't too bad. Sometimes it's kind of a pain. It really depends on the matrix A that you're starting with. But for 2x2s, this speedy trick works. And then the other thing is that you can just ask a computer for the inverse of a matrix. It's not a terrible thing to do. Computers are quite good at it. And they do this. They do this procedure. They just do the arithmetic very quickly. So that is where I'm going to leave it for this class. You have now made it through pre-calculus. I want to tell you in parting that there are some things we haven't discussed this semester, which if, in an ideal world, I would have discussed with you. The first is sequences and series. And I will be giving you a little video lecture on those. And that's, again, just about notation. I want you to learn the sigma summation notation. The others, and some of this is not normal at Santa Fe, some of it is, conic sections, right? A kind of geometric study of parabolas, hyperbolas, and ellipses. Those objects, which we usually think of as having equations, can also be thought of as purely geometric objects, like a collection of points that satisfy some distance restrictions. So stuff to be aware of. For calc. Sigma summation notation. And I will post a video lecture on this. And this will be on final. Only in the gentlest possible way, like questions that just ask if you understand the notation. So I'm not going to give you a big homework set to work on this. I just want to post a video explaining the notation and then verify that you've learned the notation, because this shows up in Calc 1 a little bit, in Calc 2 a lot of it, and the biggest hurdle there is usually just getting people past the notation. Conic sections. Specifically, there's really only one thing that you'll need in calc from that section, and that's the equation of a circle. Now, I think probably most of us see this. It's definitely taught in 1033 and 1105. Most pre-calc classes do a little discussion of conics, and it usually honestly goes way past what you need in calculus. You don't need that shit in calculus beyond knowing the equation of a circle. But you should know the equation of a circle. Right? If you don't know this from a previous algebra class, I recommend it. The other thing, and this is not a part of the curriculum here at Santa Fe, but it was back in the day when I took pre-calc. And I used to put it in my pre-calc class, but had so much trouble with people understanding the polynomial section, I stretched out polynomials and stopped doing partial fractions. This is not going to show up at all in Calc 1, and I think that's why Santa Fe doesn't do it. But it does show up in multiple places in Calc 2. Partial fractions is a little bit weird, and your Calc 2 teacher will teach it to you in detail. But I just want to let you know, stuff to be aware of for Calc. These are some algebra topics that I would love to shove into this class if we had more time. I'm going to shove one more in, right? The sigma summation notation. Conic sections, genuinely not very important, but the equation of a circle is something you should know. And then partial fractions, not an official part of the class here, but something I would really like to have be a part of the class. And if you want to excel in your calc class, I recommend doing a little self-study on each of these topics. They are all in your textbook. There are also a million YouTube videos on each of them. So between now and when you take calculus, I would recommend reminding yourselves a little bit about these things. The only one of these that will show up on the final is the summation notation, stuff on series and sequences, which again, video lecture. Conics, not going to beat you up on it. Partial fractions, not even a part of the class here at Santa Fe, but goddamn, it should be. That's it from me, guys. So it's been a wonderful semester, and I want to thank you. So many of you have put in so much work and done such a wonderful job communicating with me. So if there's anything that I can do to help you as you move forwards in your career, please let me know. Make sure you prepare yourself for the final exam. Remember, your final exam is on the 9th at 10:30 a.m. It's not the normal time for our class, so you want to put a few alarms in your phone for that. And remember, the final can only be done online, cannot be done at the testing center. So please don't show up there expecting them to let you do it. They won't. That's it for me right now. Yeah, so Whitney, what's up? You can type to me if you like here, or if you need to talk privately, maybe we can do it elsewhere.
I didn't know if you got the email that I sent you, or if you've seen the email that I sent you.
Let me take a look, see.
Just because I didn't know if it was possible to get a late withdrawal within the class.
I remember you saying we're going to email on Tuesday, but I don't have anything here from you. Let me take a look. Yes, under certain circumstances, I can withdraw students late. but not always. It depends on a few different things, but I should be able to check if I can. Let me take a look. Turn this off real quick. Okay. Section 8. Yeah, Whitney, your SFID ends in 9678, is that correct?
Yeah.
Yes, I do have the ability to withdraw you from the class. I think today is probably the last day I can do that. The last day the class meets is usually the deadline for me to do this. Is that something you want to do?
Yeah, I just think maybe this semester wasn't the semester for me to take pre-calc.
I hate to see something like that happening when it isn't necessary. Oh, but I do see here, yeah, so those first 2 exams were a little rough. How did you feel the 3rd exam went, or did you take the 3rd exam?
I didn't take the 3rd exam.
Okay, then, yeah, probably this is the right move then. I can go ahead and withdraw you from the class then, sure, if that's what you want. Do me a favor, just because I shouldn't do this without having some sort of documentation. If you could send me another email, because it looks like that first one didn't come through, just kind of formally requesting that I do. I'll go ahead and do it now, but that way I've got a paper trail. Is that okay?
Yeah, I can do that.
All right, thank you very much. I'll go ahead and do this right now, and then you'll be all set.
Thank you so much.
Of course, of course.
Bye.
Take care. Oh, date incomplete. I need to put in a date. Okay. Jimmy, did you need to talk to me about something?
No.
All right.
Thank you for being my professor this semester.
Yeah, of course.
Take care.
You too.